All right, so you want to understand algorithms, and more specifically, the ones that use binary trees. Well, we've got a whole stack of notes and code right here, even some algorithm theory in Chinese. So in this deep dive, what we're going to do is we're going to decode all of it and see what insights we can unearth, especially about how they're used in something you use every single day, search engines.
Oh, wow. Sounds like a fascinating journey. Yeah, binary trees, they're quite elegant in their structure
No.
and also incredibly powerful in how they can be applied.
Okay, so we've got these Chinese lecture notes, Horgeuser, and a whole bunch of code examples, mostly focusing on binary tree traversals, and then also some pretty interesting real-world problems. Before we get lost in the code, though, maybe you can translate and summarize some of the key points from those Chinese notes for us.
Absolutely. So these notes, they really highlight the core principles of algorithms, especially the power of recursive patterns. Now, recursion, it can be a bit tricky to grasp at first, but it's basically about breaking a problem down into smaller, self-similar pieces, kind of like those Russian nesting dolls, where each one contains a smaller version of itself.
I get the nesting dolls analogy, but how does that apply to binary trees, though?
Well, in a binary tree, you see, each element is called a node, and each node can actually be treated as the root of its own subtree. So what we can do is we can apply the same logic recursively to traverse the left and right subtrees, making the problem solving much more efficient. Now, these notes also dive into two key search algorithms, depth first search, or DFS, and breadth first search, BFS.
TFS and BFS, I've heard those terms thrown around quite a bit. Can you break them down for me?
Sure. Think of exploring a maze. With DFS, what you do is you pick a path and you keep going until you hit a dead end. Then you backtrack and you try a different path. It's like going deep into the branches of a tree before exploring its width. Now, BFS, on the other hand, that's like exploring the maze layer by layer. So you check all paths connected to your starting point first, then all paths connected to those, and so on. It's like exploring the tree level by level, starting from the root and moving outward.
So DFS dives deep and BFS goes broad. How do we know which one to use, though? What are the real-world implications of choosing one over the other?
Well, the choice really depends on what you're trying to achieve. Let's say you're searching for a specific file on your computer, if you know it's buried deep, within a specific folder hierarchy. Then DFS might be the best bet. But if you're looking for any file with a specific keyword, regardless of its location, then BFS would be more efficient because it explores all folders at a given level. Before moving deep,
That's a great way to put it. Seems like choosing the right search algorithm can save you a lot of time and effort. Now, the lecture notes also mention something about the logic of recursive functions. Can you elaborate on that a bit?
sure. So recursive functions, they work by calling themselves within their own definition. They have what's called a base case, which stops the recursion, and a recursive step, which breaks the problem down further. Understanding what happens before, during, and after that recursive call is crucial to really grasping the elegance and power of recursion.
Okay, that makes sense. So we've got the theory from the Chinese notes. Now we're ready to dive into the code and see how these concepts actually work in practice.
Yeah.
You mentioned binary tree traversals earlier. Can you give us a quick rundown of what they are and why they're important?
Sure. Binary tree traversals, those are algorithms that visit each node in a tree in a specific order. They're essential because they provide a systematic way to explore and process the information stored in the tree. Now we have three main types: pre-order, in-order, and post-order.
Interesting. I'm guessing each type of traversal has its own unique purpose and application.
Exactly. Take in-order traversal, for example. If we apply it to a binary search tree, it visits the nodes in ascending order. It basically turns it into a sorting machine. This is incredibly useful for tasks like searching for a specific value or finding the minimum or maximum value in the tree.
Wow. So it's not just about visiting the nodes, it's about the order in which we visit them
Yeah.
and how that order can be leveraged to solve specific problems. That's pretty neat. Let's dive into some of the code examples you have and see how these traversals work in practice.
Sounds good. Let's start with pre-order traversal, which follows a simple pattern. Visit the root node first, then recursively traverse the left subtree, and finally, recursively traverse the right subtree.
Okay, so it's like root, left, right. What does the code look like for that?
Let's take a look at a Python example. Python def preorder traversal self root optional tree node def listen. Def preorder traversal self root dot self dot dfs root. Res def preorder traversal self root dot self root res def preorder traversal self root res def self root res if not root return if not root res dot attend root dot dfs if not root dot self dot dfs root dot root res.
All right, walking through this, we first create an empty list called a root
Hmm.
to store the traversal results. Then we call the DSS function, passing in the root of the tree
Yeah.
and our empty list.
Yes. And the magic happens within the DFS function. If the root is empty, meaning we've hit the end of a branch, we return an empty list. Otherwise, we add the value of the current root to our result list. Then the function calls itself, first with the left child of the current root, and then with the right child. This recursive structure ensures that we visit all the nodes in the correct root left-right order.
So we're basically applying that same root left-right logic to each subtree, recursively visiting every node.
And building up our results list. This pre-order traversal seems pretty straightforward. What makes it so useful? What kind of problems can we solve with it?
Well, pre-order traversal. It's particularly useful for tasks like serializing a tree, which means converting its structure into linear format that can be easily stored or transmitted. It's also often used for cloning or copying a tree, as it allows you to recreate the tree structure by simply following the order of the nodes in the pre-order traversal.
That's fascinating. So we've gone from understanding the core principles of algorithms to diving into a specific traversal technique and even seeing how it can be applied to solve real-world problems. I'm starting to get a sense of how powerful these concepts are.
I hit it quite impressive, yeah. How seemingly simple concepts like visiting nodes in a specific order can have such profound implications. And we've only just begun to explore the world of binary trees and algorithms.
I'm definitely eager to learn more. Let's move on to the next type of traversal.
All right, so we've tackled pre-order traversal. What's next on our binary tree traversal tour?
Let's explore in-order traversal, which, as you might have guessed, visits the nodes in a slightly different order. Left subtree first, then the root node, and finally the right subtree.
So instead of root left right, it's left root right. I'm curious, what kind of impact does this change in order have on the output or the types of problems we can solve?
One of the coolest things about in-order traversal is what happens when you apply it to a binary search tree. Remember, in a binary search tree, all the nodes in the left subtree are smaller than the root, and all the nodes in the right subtree are larger.
Right, that's like a tree that's already sorted in a way.
Exactly. And because of this special property of binary search trees, in-order traversal spits out the nodes in ascending order. It's like a built-in sorting mechanism.
Sounds pretty slick. So if you need to quickly get a sorted list of values from a binary search tree, in-order traversal is your go-to algorithm. No need to implement a separate sorting algorithm. I'm guessing this comes in handy in search engines.
Absolutely. Search engines often use binary search trees to store and organize massive amounts of data. When you make a search query, the engine can use in-order traversal to quickly retrieve a sorted list of relevant results.
Wow, that's a great example of how these seemingly abstract concepts have real-world applications. Do you have a code example of in-order traversal that we could look at?
Of course, here's the Python code for in-order traversal.python. Traversal self in order traversal self root dot ewarts in order dot listened def in order traversal traversal self root dot dfs fix def in order traversal self root dot return res dot def dfs self root res if not root return if not root dot self dot dfs root dot left res if not root dot res dot append root dot eval if not root dot self dot dfs root dot right res.
This looks very similar to the pre-order code. What's the key difference here that makes it an in-order traversal?
You're right. The structure is very similar. The subtle but crucial change is the position of rs.append, root.val. In pre-order, we added the root's value to the list right away. Here, we do it after traversing the left subtree. But before traversing the right subtree, this ensures that all the smaller nodes in the left subtree are processed before we visit the root. And then we move on to the larger nodes in the right subtree.
So it's all about the precise placement of that one line of code. That determines the order of the traversal. That's fascinating. All right, we've covered pre-order and in-order. What's the last type of traversal we need to explore?
The final member of our traversal trio is post-order traversal, as you might imagine. It visits the nodes in yet another order. Left subtree first, then the right subtree, and finally the root node.
Left, right, root. It seems like we're saving the best for last, visiting the root node, only after we've explored its entire subtree. I'm curious about the situations where this type of traversal really shines. What kind of problems lend themselves to a post-order approach?
Well, post-order traversal is particularly handy when you need to process the children of a node before you process the node itself. Think of tasks like deleting a tree or evaluating mathematical expressions represented as trees.
That makes sense. If you're deleting a tree, you want to make sure you've dealt with all the subtrees before removing the root. And for mathematical expressions, evaluating the sub-expressions first before combining them at the root. Seems logical. It's all about respecting the hierarchy of the tree and processing the information in the right order. Do you have a code example for post-order traversal as well?
Absolutely. Here's the Python code for postorder traversal.python.def postorder traversal self root optional tree node def listened def postorder traversal self root.return res.def dfs self root res soast def poster traversal self traversal.def dfs self root res if not root.return if not root.dfs root.left res and not root.res.append root.val. Again, the overall structure looks very familiar. So the key difference here must be, the position of rs.append root.val yet again. Now we're adding the roots value to the list, only after we've traversed both the left and right subtrees.
You got it. This simple change in the order of operations ensures that we visit all the nodes in the left subtree, then all the nodes in the right subtree, and finally the root node. It's like a bottom-up approach to exploring the tree.
Okay, so we've covered pre-order, in-order, and post-order traversals. We've seen the code, and we understand the order in which they visit the nodes. But I'm really curious to see how these traversals are actually used to solve more complex real-world problems. Do you have any examples of that?
Of course, these traversal techniques, they're like building blocks. We can use them to construct more sophisticated algorithms for solving all sorts of interesting problems. For example, let's say we want to validate whether a given tree is a valid binary search tree. We can leverage the properties of in-order traversal. To do that quite elegantly.
Wait, hold on. How does traversing the tree in a specific order help us determine if it's a valid binary search tree?
Remember that in-order traversal of a binary search tree visits the nodes in ascending order. So, if we keep track of the previously visited node during the traversal, we can easily check if the current node's value violates this ascending order. If it does, we know we don't have a valid binary search tree.
Ah, I see. We're basically using in-order traversal to perform a real-time check of the binary search tree property as we visit each node. That's clever. What does the code for this validation algorithm look like?
Here's a Python implementation. Python dst.def is valid bst self-root. Optional tree node dsbrew. Df is valid bst self-root. My yes, my min, my max is valid bss. Root def is valid bst self-root. Return my yes. Def dfs root if not root. Return true flow left min left max. Self.dfs root.left if not root right boo right min right max. Self.dfs root.right if not left boo or not right boo. If not left boo or not right boo. Return false 0 0. If root.left and left max equals root.val, or root.left and left max root.val, or root.right and right min root.val, return false 0 0. If root.left and left max root.race, or root.right and right min self.decertain. If root.left and left max equals root.val, or root.right and right min root.val, left and max root.val, right max.
This code is definitely more complex than the basic traversal example we saw earlier, but I can see how it's building upon the concept of in-order traversal to accomplish a specific task. We're recursively checking if each subtree is valid, and we're also making sure that the current node's value falls within the expected range based on its position in the tree.
You got it. It's a great example of how we can combine traversal techniques with other logic to solve more intricate problems. And this problem of validating binary search trees, it comes up quite frequently in various applications.
That's cool. It's amazing how something as seemingly simple as visiting nodes in a specific order can be used to perform such an important verification task. I'm starting to see how these traversal techniques are like Swiss Army knives for working with binary trees. Do you have any other examples of how they're used in practice?
Of course. Remember how you mentioned search engines earlier? Well, let's say you want to build a search engine that can handle more complex queries, like finding the longest consecutive sequence of words in a document.
Now that sounds challenging. How would we even represent a document as a binary tree? And how can we leverage tree traversals to find consecutive sequences?
Well, representing an entire document as a binary tree might be a bit complex, but we could certainly represent specific aspects or features of the document as a tree. For example, we could build a tree where each node represents a word and the connections between nodes represent the order in which the words appear in the document. And to find consecutive sequences, we could use a modified depth-first search approach.
A modified DFS. What would that entail?
Imagine we're traversing the tree, and at each node, we keep track of two things: the length of the longest increasing consecutive sequence starting at that node, and the length of the longest decreasing consecutive sequence starting at that node. We can update these lengths as we traverse the tree, considering both the left and right children of each node.
I'm starting to see how this could work. As we visit each node, we check if its children can extend the current consecutive sequence, either increasing or decreasing, and at the end, we just need to find the maximum sequence length we've encountered.
Exactly. It's a clever way to leverage the structure of a tree and the systematic exploration provided by DFS to solve a non-trivial problem.
This is really exciting to start to appreciate the power and versatility of tree traversals. They're not just about visiting nodes. They're about extracting meaningful information from the tree and using that information to solve problems. Do you have any code examples for this consecutive sequence problem? I'm eager to see how it all comes together in practice.
Of course. Let's look at a Python implementation of this algorithm. Python, def, long consecutive, self, root, optional tree node, manand, def, DFS node, if not node, redinkertome, node left dex, left dink, DFS node dot left, if not node, right dink, writing, does not node, occurring kerdec, 1 if node dot left plus 1 if node dot left dot left, if node dot left plus 1 equals node dot left dot val, kerdec plus left dink is node dot val 1 is node dot left dot val, kerdec for dec plus left is same if node dot right, if node dot val plus 1 node dot right dot val, quant node dot val plus 1 and node dot right dot val, kerdec, right dot plus max, occurring right node plus 1, elf node dot val 1 dot right dot 1, elf node dot right dot val, max node dot right dot 1, elf node dot right dot val, max node dot right dot val, max node dot right dot val, max node dot 1, elf node dot 1 dot right dot val, DFS root elf node dot 1 dot val 1, return right dot val, return maxlin.
Wow, that's a lot of code to process. It seems like we're doing a lot of comparisons and updates as we traverse the tree.
We are, but if you break it down step by step, you'll see how it elegantly combines the concepts of tree traversal, recursion, and the logic for finding consecutive sequences. It's a beautiful example of how seemingly simple ideas can be woven together to solve complex problems.
This is amazing. It's like we've unlocked a secret code to understanding how data is structured and processed in so many different applications. I can't believe how far we've come in just one deep dive. We've gone from basic definitions to understanding the core principles of algorithms, exploring different traversal techniques, and even seeing how those techniques can be applied to solve real-world problems.
It's been a fascinating journey so far, and we're not done yet. There's still so much to explore in the world of algorithms and binary trees. But I think it's time to shift gears a bit and consider the bigger picture. What are the key takeaways from all of this? Why should our listeners care about these concepts? How do they impact their lives?
That's a great question. We've covered a lot of ground, and it's important to step back and see the forest for the trees, so to speak. What's the big picture here?
Well, the concepts we've been discussing might seem abstract at first, but they're actually deeply embedded in the technology we use every day. Binary trees and graph algorithms are the backbone of so many systems. From databases and search engines to social networks and recommendation systems, they're the invisible forces that power our digital world.
Wow, I had no idea. So understanding these concepts is not just about academic curiosity. It's about understanding how the world around us works. It's like gaining a deeper appreciation for the intricate machinery that makes our lives so connected and convenient.
Exactly. And it's not just about understanding how things work. It's about being able to participate in shaping the future. The more we understand the fundamental principles of algorithms and data structures, the more we can contribute to developing innovative solutions to the challenges we face as a society.
That's inspiring. It's like you're saying that learning about algorithms is not just a technical skill. It's a form of empowerment. It gives you the tools to analyze problems, design solutions, and create new possibilities. I love that perspective.
I completely agree. And the beauty of it is that the journey of learning never really ends. There's always more to discover, more to understand, more to create.
You've definitely ignited a spark of curiosity in me. I'm feeling excited and a bit overwhelmed by the vastness of it all. Where do we even go from here? What are some of the next steps for someone who wants to dive deeper into the world of algorithms?
That's a great question. And it's the perfect segue into our final thoughts. Let's shift gears and explore some of the resources and directions you can pursue to continue this fascinating journey of algorithmic discovery.
So where can our listeners go to continue exploring this world of algorithms?
Well, you've already taken a great first step by diving into these materials with us. From here, there are many paths you can take. There are tons of amazing resources available online, like interactive coding platforms, where you can practice implementing algorithms and actually see them come to life.
Yeah, I've heard of those. It's one thing to read about an algorithm, but seeing it actually work and being able to tweak it yourself really takes the learning to another level.
Absolutely. And don't underestimate the power of community. There are vibrant online forums and communities dedicated to algorithms and data structures. You can connect with other learners, ask questions, share your insights, and even collaborate on projects.
That's so cool. It's like turning learning into a social activity. It's much more fun and motivating to learn with others.
Exactly. And of course, there's the good old-fashioned approach of reading books. There are classic textbooks that cover algorithms in depth, as well as more accessible books that focus on specific applications or explain concepts in a more intuitive way.
Yeah, it's like having a mentor in a book, guiding you through the intricacies of algorithms. I'm already starting to imagine myself, curled up with a good algorithms book and a cup of coffee, lost in the world of computational thinking.
That's the spirit. Remember, learning about algorithms, it's not about memorizing formulas or code snippets. It's about developing a way of thinking, a mental framework for approaching problems and finding elegant solutions.
It's like training your mind to think like a computer scientist, breaking down complex challenges into smaller, more manageable steps. And who knows, maybe one day you'll be designing the algorithms that power the next generation of search engines, social networks, or even artificial intelligence.
That's the beauty of it. The possibilities are endless. And even if you don't end up becoming a professional programmer or algorithm designer, the skills you gain from exploring this world will benefit you in countless ways.
I can see that. It's like you're saying that learning about algorithms is not just about acquiring technical knowledge, it's about developing critical thinking skills, problem-solving abilities, and a deeper understanding of how technology shapes the world around us. Those are valuable assets in any field.
Precisely. And beyond the practical benefits, there's also an element of intellectual satisfaction and even beauty in exploring the world of algorithms. It's like discovering hidden patterns and elegant solutions that reveal the underlying order and structure of the universe.
It's like you're saying that algorithms are a form of art, a way of expressing creativity through code and logic. That's a beautiful way to think about it.
I'm glad you see it that way. And remember, this journey of exploration, it's not a race or a competition. It's about following your curiosity, embracing the challenges, and enjoying the process of discovery.
Well, you've certainly given us a lot to think about and explore. This deep dive has been an incredible journey, and I can't thank you enough for being our guide through the fascinating world of algorithms and binary trees.
The pleasure was all mine. And remember, this is just the beginning. There's a whole universe of algorithms waiting to be discovered.
And to all our listeners out there, we encourage you to continue exploring, experimenting,
And learning. Who knows what amazing things you might create with the power of algorithms. Until next time, happy coding!